Hello, and welcome to Mr. Faye's Science Basement, where today we're going to be talking about fossils. And when people think about fossils, they usually think about things like this. So let's go ahead and get started. In the Google Classroom, you have a sheet that's been made available to you. It looks like this sheet over here on the left. This is going to be a template for our discussion that we're going to have today. There are a couple things you can do with it. I suppose you could fill it out digitally if you like, just using the copy that I've given you in the Google Classroom. Two, if you have access to a printer, feel free to print it up and take some notes on it by hand. You could actually cut it out and stick it into your scrapbook. Or three, if you are confident taking your notes freestyle, feel free to do that. Take out a sheet of paper, pen, pencil, markers, whatever it is you want to do. Jot down some information, do some sketching, and pause the video at any time to help you do that. So let's get right to it. We're talking about fossils, and fossils are really any preserved remains of something that was once alive, especially referring to things that are prehistoric. And something that's fascinating about fossils is when we look at fossils, we tend to find things that are really different from what exists on the earth today, which allows us to infer that things have changed over time, because the evidence of all of the animals and plants that live in this area are actually really different than what we have existing today. Actually, if you look down in central New York and you start to dig down into fossil layers, go somewhere like Chittenango Falls would be a great example, where you have this layered sedimentary rock. All of the fossils that you find are aquatic. In fact, they are saltwater aquatic, and they give evidence of life in a shallow saltwater environment, very different than what we have in central New York today. And most of the species that we find actually no longer exist on Earth, which is fascinating when you think about it. So we do have these types of fossils, which are the types that you think of, either imprints or casts in sedimentary rock. We also can get some imprints or shadowing of leaf structures and things like this. You actually see something really similar to this if you have leaves that spend the winter on a concrete sidewalk. Very often you'll find, if you peel it away, a little bit of a discoloration on the actual cement itself. And that's pretty similar to how fossils actually form. That little layer is chemically different. And if you were to layer some other layers of sedimentary rock on top of that, under just the right conditions, you can get some really good preservation. Now, when folks think of fossils, this is normally what they think about. They think about dinosaur bones. Dinosaur bones make up a portion of the fossils that we have, but does not by far make up most of them. We actually have thousands and thousands of examples of species other than dinosaurs that we find all the time, actually indicating that over 99.9% of all the life that ever existed on the planet is most likely extinct now, because of all these examples that we find of species that don't exist today. Dinosaurs you can find in the United States. So we have hundreds, actually borderline thousands of species that we do find in the United States every day. You happen to see ones that are fully articulated in museums. But if you watch that video on Dinosaur National Monument, you realize that some people can find dinosaur bones simply laying around or by excavating the earth just a little bit, which is pretty cool. We do find other things also, such as imprints. Now, this is a great example of how scientists can start to infer things about life. Looking at dinosaur footprints, there's a lot you can speculate on: how much they weigh, by how much they stick into the mud, how fast they can run, depending on like the gait and the distance between footprints. So there is a lot that you can figure out simply by looking at that fossil record. Now, preserved in stone is not the only type of fossil that we have. We actually can preserve them in other things too. And some of these are fascinating. Many of you in sixth grade actually learned about Iceman. Okay, we have human pre-human specimens that we can find that are actually preserved in ice. And if you look, they still have like tissue on the bones too, which is kind of interesting. That tissue you can go into and take a look at not just the structure, but you can also see chemically protein structures. And in some cases, you can actually find just recently, this was discovered, somewhat preserved DNA molecules, which is kind of wild. One of the more interesting and local examples of this is the mastodon, or basically the woolly mammoth, Manny from Ice Age. We actually find mastodons around here in New York State. In fact, if you were to go down to Ithaca or Letchworth State Park, go down the Hudson Valley, you can actually see preserved specimens, mainly bones, of articulated woolly mammoths that were here not too long ago. And in fact, if you take a look at this one right here, sometimes they find them really well preserved with hair on them and everything. Now, how can this happen? Well, you can find them in the polar ice caps, where they're really well preserved, but you can also find them partially preserved in swamp and marsh areas due to the acidity of the substrate or the soil that's in there. So we definitely have some pretty cool pieces of fossil evidence if you dig around a little bit. All right, so let's take a look back at our sheet. If you take a look at the notes that we're taking, we've gone over a couple examples of different types of fossils that you can have. And again, the most interesting thing about this is that when we find fossils, they most often are fossils that do not exist today. In other words, they are representative of a time on Earth that was different than the time we have now. And for many folks, that's pretty compelling. All right, so those are some examples. What we're going to do is we're going to direct our attention down here at the bottom, which is a little bit more complicated. We're going to take a look at the correlation of the fossil record. In other words, how can we take all of these thousands and thousands and thousands of examples of fossilized remains and start to correlate it into like a time frame or a story of how the Earth could have progressed through the natural history timeline. And we're going to look specifically at something called relative dating first. All right, so the first type of relative dating that we're going to take a look at is takes place in sedimentary rock, and it has to do with layering. And this is going to be something that many of you understand from sixth grade and some of the things that you learned when you learned about the rock cycle. We're fortunate to have a lot of sedimentary rock around where we live. And it's actually in that sedimentary rock where we find fossils of life that existed in an ancient ocean. And what relative dating is not putting an exact year on when these fossils existed, but it does give us a sense of the order in which the fossils existed. A great example can be seen here on this image over here that you can see on the screen, kind of right in the center. Keep in mind, this image is down here on your sheet and you have an area to write over to the right of it. So as you're taking a look at this diagram, this represents the different layers that you have of sedimentary rock. Okay, so we have 1, 2, 3, 4 layers of sedimentary rock. And for those of you who remember the rock cycle, sedimentary rock is laid down by, of substrate of different years on top of each other. So you'll have some erosion that puts something down, and then the next season you'll have some erosion that pushes something down, and you wind up with this erosion giving you all the layers on the top. I'm probably doing this too much with my hands, but it's kind of fun. These layers build as you go. So the oldest layer winds up on the bottom, and the layer that was last put on is the one that's on the top. Now, sedimentary rock takes a long time to form, which is actually pretty cool, because if we look in the lowest layers, layers have remains that are different than the most recent layers. So because of that, we can start to infer that the oldest rocks that you have down here also have the things that were alive at the time, or the oldest fossils. Okay. And as you move your way this way, this is going to be ugly because I'm using a mouse to do this. As you move your way this way, actually, that's not that bad. As you move your way up, and put these layers down. This is the next layer, and these are the next things that appeared to exist. This right here is the next layer, that's the next layer, and that's our most recent layer. So as you go down in the layers of sedimentary rock, you can figure out that that lived before that, which lived before that, which lived before that, which lived before that. So these would be our most recent. And we find this same similar progression as we look at sedimentary rocks around the world. So, in addition to looking at these layers and trying to put the order in which things existed together, we can also find really, really, really interesting geological things happening. So, for example, and this is pretty loose, and just kind of as an example, I want to show you. There are areas in the fossil record where we will see certain organisms alive, and then we'll pick up something that could be evidence of a major geologic event. So a great example would be you find a type of species that exists all the way through here, but then all of a sudden at this point right here, you have a huge layer of, let's say, volcanic ash. Okay. So after that huge layer of volcanic ash, you might find that species that existed down here now all of a sudden disappear from the fossil record. So sometimes this marks the end of major periods of growth in that natural history timeline, and sometimes these indicate like a mass extinction, which is kind of cool. Something else we could take a look at, which is interesting, is kind of builds on something that many of you know from sixth grade too, and that's the concept of Pangea and plate tectonics. So if you go back into the fossil record or into the natural history timeline about 300 million years, many of you know that the continents were all in one large mass called a supercontinent or Pangea. Something that's interesting and kind of correlates with what we were seeing on that last slide is that we find certain fossils, especially of dinosaurs will work with this right here. We'll find certain species of dinosaurs, fossils on the South American coast, and we'll find the exact same species of dinosaurs today. We'll find their fossils on the African coast, which again is interesting because it shows that the dinosaurs that might be in question existed in this region of Pangea. Now, this is cool for one reason, actually for multiple reasons. One, it helps to support the idea of Pangea and plate tectonics, but it also gives us a time frame of when this species would have existed. So if you have a species that exists here in South America and here in Africa, that means you can correlate it with when Pangea actually split apart. So that gives you a cool geological marker. If you have species that exist over here and don't exist here, we can infer that they were on Earth after the splitting of the continent, which is kind of cool. Incidentally, that's why we have so many different types of species in Australia, or at least that's the theory, is because Australia was quick to kind of break off and become isolated. So those are species that came about after Australia was attached to anything. When you look at Australian animals and plants that exist today, they're very different than the rest of the continents, which is kind of an interesting thing all by itself. So the two examples that we just saw are examples of relative dating. In other words, correlating the order in which things were alive on Earth, and also correlating that sometimes against geologic events like meteor strikes or volcano eruptions, or even plate tectonics like Pangea and things like that. One of the more difficult things to understand, which I'm going to attempt to do now, is talk to you a little bit about how absolute dating works. Now, what absolute dating is simple. It's putting an exact year, or at least an exact time frame, onto the age of a specimen. In other words, digging up a bone and saying that existed 1 million years ago, let's say. Okay, that is absolute dating. Come up with an absolute time frame of when that thing existed. But the way that happens is a little bit complicated, and I'm going to do my best to make it relatively simple. And to tell you the truth, my understanding of it is partial. So hopefully I'll do a pretty decent job here. So we're going to take a look at this example of absolute dating, or how you can put an absolute or accurate date on things using actually radioactive isotopes, which sounds weird. And I'll give you a little crash course on that in a second. But we're going to direct our attention down here to this part of the page if you have the page in front of you. All right, so here it is in the nutshell. And I'm going to use carbon-14 as an example because it is the one that I understand the best. So radioactive isotopes are unstable and they break down over time. And what's cool about that is we know exactly how long it takes for radioactive isotopes to break down. So for example, carbon exists as carbon-12. In other words, it's a carbon atom that weighs around 12 AMU, has 6 protons and 6 neutrons, is stable. However, carbon-14, which has 2 extra neutrons on it, is not stable, and it breaks down. And about half of it will break down over the course of about 6,000 years. So by looking at the weight or the atomic mass of carbon in something, you can figure out how long ago it formed by how much of the carbon-14 has broken down. Okay, so in other words, you do a carbon-14 test. What's the percentage of carbon-14 that exists in that specimen, and you can figure out how long ago it formed and began to break down. Now, I'm going to go one step deeper and try to show you how this happens for those of you that are interested, because I'm interested. I think it's pretty cool. So here's how it works, and it involves the sun, believe it or not. So when you look in the atmosphere, most of the atmosphere of the Earth is made up of nitrogen. Okay, about 78% of it is made of nitrogen. And nitrogen has 7 protons, 7 neutrons, and has an atomic mass of 14 AMU. That's normal nitrogen. That's what nitrogen, not a radioactive isotope, that is what normal nitrogen has. In fact, most of it is not radioactive and looks just like that. However, some of the cosmic rays from the sun can bump into nitrogen atoms and actually remove some of their protons. And here's how this works. And again, it's strange. You have a nitrogen atom that has 7 protons in it, and you'll get a cosmic ray or some radiation, some electromagnetic radiation coming from the sun, smacks into the nitrogen molecule and knocks off a proton. So then it only has 6 protons. Now, this is weird, but elements are defined by the number of protons that they have. So that cosmic ray actually turns nitrogen into carbon. But when it knocks the proton out, it actually replaces it with a neutron, which again is very strange. So you have carbon because it only has 6 protons, but it has the original mass of 14 because of that extra neutron that it has. That carbon-14, not normal carbon, which is 12, but that carbon that now weighs 14 is unstable. And it will break down. About half of it will break down every 6,000 years. So here's what's happening. If you have an animal like this animal right here, and it's eating plant matter, okay, that plant matter is taking carbon-14 atoms from the atmosphere and putting it into carbohydrates that end up getting eaten by the animal. Okay, so there you get a certain percentage of carbon-14 that's formed every day by the sun hitting it with these rays. However, when an animal dies and stops eating carbon, with some percentage of it being carbon-14, the carbon-14 then starts to break down. It's in the ground. The nitrogen is no longer getting excited by cosmic rays and turning into carbon-14. So those remains actually have the carbon-14 break down. If you look at the percentage of the carbon-14 that's in that specimen, you can go back and do some math and figure out how long that specimen stopped living and stopped bringing in the normal amount of carbon-14. So that was probably way too deep of a discussion, but what it does is it allows us to pin time frames in years onto many of the specimens that we have. Now, some of you are thinking, whoa, carbon's only 6,000 years. What do you use for different specimens? We can actually use different radioactive isotopes to do those, but carbon-14 is the one that's most often referenced. All right, so there we go. That was our discussion of fossils. And again, when we take a look at fossils, we see one, evidence of things that existed that don't exist today. Two, we can correlate them into an order by looking at layers and judging them against major geological events. And three, we can use absolute dating, using radioactive isotopes, to come up with the actual age range of the specimens that we find. So hopefully that has helped you out a little bit. Hope you enjoyed Mr. Fay's Science Basement. That's everything you'd ever want to know, and probably more, about fossils.